Let's work through a Newton's method problem together. So here are the directions. Use Newton's method on the following function and initial guess. Continue iterations until you reach 5 decimal points of accuracy. And the function is f of x equals x squared minus 10, and the initial guess is x sub 0 equals 4. Okay, so first of all, just a very quick review of what Newton's method is. We use Newton's method to approximate the roots of a function. The roots are also known as the zeros or the x-intercepts. So essentially what I'm going to be doing is I'm going to be approximating a solution to 0 equals x squared minus 10. Now this particular function, x squared minus 10, we actually don't need to use Newton's method on that, right? We can easily solve this equation for x just by moving the 10 to the other side and taking the square root. We'd get a solution of plus or minus root 5. But we're going to practice using Newton's method, and then the nice thing is that this example will actually be able to compare our approximation to the exact solution and kind of see how accurate it is in this case. Now also here, there are two roots, right? Plus or minus root 5. But since we're doing this initial guess of 4, we're just going to be approximating the positive root. Okay, so first, let me just write down the formula for Newton's method. So remember the formula looks like this. X sub n plus 1 equals x sub n minus f of x sub n over f prime of x sub n. Okay, so then, it looks like we're going to need the derivative, right? We have to calculate the derivative at certain values of x. So my derivative then here, I'll just write it out to the side here, is 2x. So nice simple derivative in this case. All right, so let's go ahead and start with our first iteration. Okay, so if we follow our formula, so we have x0, we want x1. So x1 is going to equal x0 minus f of x0 over f prime of x0. Okay, now x0 in this case was 4, so this is going to be 4 minus f of 4 over f prime of 4. Okay, and for this example, I've already calculated a lot of these function values and derivative values just to save ourselves a little time. To calculate these in general, you're just going to be using a calculator, right? So to calculate f of 4, I'm just taking 4 and plugging it into f of x, for example. So in this case, then that would be 4 squared minus 10. Okay, so 16 minus 10, so that's 6. And then for f prime of 4, the denominator, I'm taking 4 and plugging it into the derivative here. So if I plug in 4, I get 2 times 4, which is 8. So here I've got 4 minus 6/8, which ends up being 3.25. Okay, so often that first iteration will end up giving you a pretty nice value, but after that you're going to get long decimals, and you're pretty much just going to have to use a calculator or a computer to calculate these iteration values. But anyway, we have one iteration now. 3.25 is our new guess. Okay, so that we can use that to calculate x2. Okay, so x2 is going to be x1 minus f of x1 over f prime of x1. Okay, so that's 3.25 minus f of 3.25 over f prime of 3.25. Okay, and let me write this out. If you plug that in, so we have 3.25. If you calculate f of 3.25, so that's taking 3.25 and plugging it in for x in the original function, you are going to get 0.5625. And then if you take 3.25 and plug it into the derivative, well, you're just multiplying it by 2, right? So that's just 6.5. Okay, so that gives us approximately 3.163462. Okay, once again, that's approximate, right? Because there's a lot more decimal places and I'm cutting it off. So here's our x1 and here's our x2. All right, and then we just continue this process. So remember that the directions say continue iterations until you reach 5 decimal points of accuracy. So in the context of Newton's method, what that means is that until 5 decimal places don't change between subsequent iterations. Okay, so let's keep going. x3 is going to be x2 minus f of x2 over f prime of x2. Okay, and that is 3.163462. That's our previous x2 minus f of that. Okay, if I take that in and plug it into the original function, I get 0.007492. If I plug it into f prime, I get 6.326924, and that gives me overall 3.162278. Okay. So if I compare that to the previous iteration, x2, I don't have 5 decimal points of accuracy, right? The first 2 decimal points stayed the same, 0.16, but I want 5 to stay the same before I stop. So let's try it again. x4 is going to be x3 minus f of x3 over f prime of x3. Okay, so x3 was what we just got, 3.162278 minus f of x3, so I'm taking that 3.162278 and I'm plugging it into my original function, x squared minus 10, on the calculator or the computer. And we get a very small number. Okay, so what we get is 2.149284, but that's times 10 to the negative 6. Okay, so very small number. And then if I take that 3.162278 and plug it into the derivative, which is 2x, I get twice it, so 6.324556. And if you work that out, what you're going to get is 3.162271, approximately, right? These are all, I'm cutting all these off and rounding, but okay, so take a look. So above I got 3.162278, and now I've got 3.162271. So I have the 5 decimal points staying the same, right? And that's what I was looking for. Okay, so then I'm going to stop. So continue iterations until you reach 5 decimal points of accuracy. So then my approximation would be 3.16227. And then remember, in this case, this is one where we can actually solve for the exact solution. So my original equation was x squared minus 10. Okay, so I get 10 equals x squared. So my solutions for x are going to be plus or minus root 5. Now, of course, this is approximating the positive root. And if you put root 5 into your calculator, oh, sorry, not root 5. I don't know why I wrote that at all. Root 10 is what I mean. Plus or minus root 10. And if you put root 10 into your calculator, what you're going to get is 3.1622776, and then it keeps going. So we see that we did pretty good, right? We have those first 5 decimal places, and they're actually the same as if you approximated root 10 there. So hopefully this gives you a good sense of how to approach Newton's method.